In section 6.3, we'll be talking about volumes of cylindrical shells. Now, some volume problems are very difficult to handle by the methods of the preceding section. So for instance, let's consider the problem of finding the volume of the solid obtained by rotating about the y-axis the region bounded by y is equal to 2x squared minus x cubed and y is equal to 0, which is in figure 1. Now, if we slice a perpendicular to the y-axis, we would get a washer. But to compute the inner radius and the outer radius of the washer, we'd have to solve the cubic equation y is equal to 2x squared minus x cubed for x in terms of y, and that's not easy. Now, fortunately, there is a method called the method of cylindrical shells that is easier to use in such a case. So if you take a look at figure 2 up here, it shows a cylindrical shell with an inner radius of R1 and an outer radius of R2 and a height of h. And its volume is calculated by subtracting the volume 1 of the inner cylinder from the volume V2 of the outer cylinder. So you would say that V is equal to V2 minus V1, and the volume of cylinder 2 is pi r subscript 2 squared h minus pi r subscript 1 squared h. You can factor out the pi, you can factor out the h, and what's left is r squared subscript 2 minus r squared subscript 1. Now, this is the difference of squares, so therefore we can then factor it. So now we have pi times r2 plus r1 times the quantity r2 minus r1h. Then we get the following. Now, we know that anything can be 1. So that's the reason why you see this 2 pi times r2 plus r1 over 2 times the height times r2 minus r1. Now, if we let delta r, or the thickness of the shell, equal r2 minus r1, and we can let r equal 1/2 r2 plus r1, then the average radius of the shell, then this formula for the volume of the cylindrical shell becomes the following. It is V, which is equal to 2 pi r, and this 2 pi r should look familiar because it's called the circumference. Then you have h, which is its height, and then you have delta r, which is its thickness. Now, if we want to explore this a little further, we're going to let S be the solid obtained by rotating about the y-axis, the region bounded by y is equal to f of x, where f of x is greater than or equal to 0. We have a horizontal line where y is equal to 0. We have x is equal to a, x is equal to b as our upper and lower limits, where b is greater than a and it's greater than or equal to 0. And then we can see what this three-dimensional figure looks like. Now, if we divide the interval AB into n subintervals, as we've done in the past, of equal length, delta x, and then we're going to let this average of those x be the midpoint of the ith subinterval. Now, if the rectangle with the base, x subscript I minus 1 to x subscript I, and the height of f of the averages of x subscript I is rotated about the y-axis, then the result then becomes a cylindrical shell with an average radius, a height, and a thickness. So by formula 1, its volume is the following. You have V subscript I, there's your circumference, there's your height, and then there's your thickness. So in figure 4, this basically shows you the step from what's happening from one situation to the next. So here we have our graph, then we cut them into those subintervals to eventually get this particular solid. So the approximation to the volume V of that surface area S is given by the sum of the volumes of these shells. So we're going to take the sums of the volumes of those shells, and using the summation, again, there is your circumference that includes the average of those x, in this case the radius, then you have its height, then you have delta x. Now this approximation appears to become better as n approaches infinity, but from the definition of integral, we know that the following. As the limit as n approaches infinity of I is equal to 1 to n of the circumference times its height of delta x is equal to the definite integral from a to b of 2 pi x f of x dx. Thus, the following appears plausible. So here's our definition. The volume of a solid in figure 3 obtained by rotating about the y-axis, the region under the curve y is equal to f of x from a to b, is the following. There's your formula where a is in between 0 and b. So as you notice, I've kept talking about the circumference, the height, and the thickness. So the best way to remember Formula 2 is to think of a typical shell cut and then flattened, as you can see here in figure 5. So think of the shell as it's cut and then it's flattened to form this particular figure. So it has a radius x, so there's your radius. It has a circumference then of 2 pi x, so therefore there's your circumference. And then the height is represented by f of x, and then the thickness is represented by dx. Now this type of reasoning will be helpful in other situations, such as when we rotate about lines other than the y-axis.